This is architect David Barcelona. Welcome to Arkida, where you will learn anything and everything about construction. This is part 2 in the series Fibonacci in Architecture and Design. In this episode, we will be discussing the actual machinations or how to design in architecture and space planning using Fibonacci. The Fibonacci sequence or the Golden Ratio in architecture. The Golden Ratio describes the perfectly symmetrical relationships between two proportions, as can be seen on the figure on the right. Approximately equal to a 1:1.61 ratio, the Golden Ratio can be illustrated using a golden rectangle. This is a rectangle where if you cut off a square, which is the side length equal to the shortest side of the rectangle that's left will have the same proportions as the original rectangle. So, if you remove the left-hand square from the rectangle, which is indicated as number 1, you will be left with another smaller golden rectangle, which is indicated as number 2. This could continue infinitely. Similarly, adding a square equal to the length of the longest side of the rectangle gets you increasingly closer to a golden rectangle and the golden ratio. Creating a golden rectangle is pretty straightforward and starts with a basic square. Follow the steps below to create your own golden ratio. First, you draw a square. You start by drawing a square of any size. The side of this will form the length of the short side of the rectangle. Next, you divide the square. You divide your square in half with a vertical line down the center. This will leave you with two rectangles. Step 3. Draw a diagonal line. In one of these rectangles, draw a straight line from one corner to the opposite corner. Then step 4, you rotate the line. Rotate this line pivoting from the bottom or top point until it lines up with the bottom or top of the first rectangle. Then number 5, you create a new rectangle. Create a rectangle using the new horizontal line and original rectangle as guides. That is now your golden triangle. Now this relates to the Fibonacci sequence 0, 1, 1, 2, 3, 5, 18, 13, and so on, in which each term is the sum of the previous two. Plotting the relationships in scale provides us what is known as the golden spiral. This occurs organically in the natural world. So as you can see, there is a square 1, which means it has 1 unit on the top and 1 unit on the side. That goes for square 2, square 3, square 5, and square 8. Now using these squares, let us open the plan that was presented in the previous video. As you can see, it already has a rectangle, square, and various squares in different positions, meaning to say all these squares are now having the same dimensions as that of the Fibonacci sequence. Also notice that it also has connecting points. Now here is the Fibonacci series again. 0, 1, 1, 2, 3, 5, 18, 13, 21, 34, 55, 89, 144, and so on. If we take the ratio of two successive numbers in this series and divide each by the number before it, we will find the following series of number. Let's say 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 2 is 1.5, and so on and so forth. As the numbers grow bigger, you can see that the equivalent is nearing 1.618. This ratio seems to be settling down to a particular value which we call the golden ratio. So here is the golden rectangle. Here is the list where you can get adding the square. 1 by 1, 2 by 1, 3 by 2, 5 by 3, 8 by 5, 13 by 8, 21 by 13, 34 by 21. Meaning to say these are numbers which can now be attributed to the metric scale. Meaning to say 1 by 1 meter, 2 by 1 meter, 3 by 2 meters, 5 by 3 meters, and so on and so forth. So with each addition coming ever closer to multiplying by 5. So you start 1 by 1. Then you add 1. By now, it is now 2 by 1. Then you add 2 by 2. Now it is a 3 by 2 rectangle. Add 3 by 3. Now it is a 5 by 3 rectangle. Now you add 8 by 5. And so on and so forth. So the golden rectangle is a rectangle with proportions that are two consecutive numbers from the Fibonacci sequence. The Fibonacci sequence not only works on rectangles. We also have a golden triangle. So if we rotate the shorter side through the base angle until it touches one of the legs, and then from the end point we draw a segment down to the opposite base vertex, the original isosceles triangle is split into two golden triangles. Also, we can find that the ratio of the area of the taller triangle to that of the smaller triangle is also 1.618. So if the golden rectangle is split into two triangles, they are called golden triangles. Using the Pythagorean theorem, we can find the hypotenuse of the triangle. Another geometric form is called Penrose Stylings. The British physicist and mathematician Roger Penrose has developed an aperiodic tiling which incorporates the golden section. The tiling is comprised of two rhombi, one with angles of 36 and 144 degrees, which is shown in figure A, and one with angles of 72 and 108 degrees, shown in figure B. So when a plane is tiled according to Penrose directions, the ratio of tile A to tile B is the golden ratio. In addition to the unusual symmetry, Penrose tilings reveal a pattern of overlapping decagons. Each tile within the pattern is contained within one of two types of decagons, and the ratio of the decagon population is of course the ratio of the golden mean. Aside from triangles and trapezoids, we also have a pentagon and pentagram. It is a five-sided geometric form. We can see there are lots of lines divided into the golden ratio. Such lines appear in the pentagon and the relationship between its sides and the diagonals. So, designers, you now have various forms that you can play around with when doing your designs. Click the subscribe button to discover all the other videos in this site. Click the notification bell to be notified about new videos that we post. Press the like button to share this video to your friends. If you have additional comments, please post them down below or at our Arkida Facebook page, and I will answer all your queries. Thank you.